A very good evening to you. How are you? Very good, right? Okay. Today we shall continue with what we left last week. We will do the control part, okay? Robot control. And before we move to the control, I want to give you a quick review, the mental refresh for the dynamics part. Dynamics we did, before we do the we did a review for kinematics, right? And then after that, we did a Newton-Euler formulation. And then subsequently, we talk about the Newton-Lagrange formulation. And then subsequently, we give you a tutorial. Hello, it's my time to talk, okay? If you talk, and be better lower down your volume, okay? Finished, okay? And after that, we understand the Newton-Euler formulation and then Lagrange formulation are actually quite complicated. Then we give you the neural network modeling. And then now, for the control, you would imagine I give you the fundamentals. Subsequently, we share with you the single joint. And then which you would imagine would be easier, right? And then we will talk about other computer talk, Lyapunov stability analysis, adaptive control method for multiple joints. And then the fundamentals, this is the Puma with 6 degree freedom. And then this Kuka with 7 degree freedom. For the kinematics part, Chichikam part planning, which you found it's quite tedious, okay? And the dynamics is actually complicated, okay? And we will see how we can actually control with the knowledge of kinematics, dynamics, and how we can control the robot in accordance with certain prescribed performance criteria. You want your performance, your system to perform in a way you want it, okay? And you know that ChatGPT is really in fashion now, right? And ChatGPT, some part is very good, some part is unpredictable, okay? And then, so here, for this robot, is this hardware, okay? Better be safe. The ChatGPT, the guy can talk nonsense, still don't hurt you, okay? And only waste you some time, but robot cannot, if it can hurt you. Okay. Then the robot, basically, this is the robot. The environment, we have sensors, and then we do the control. Sensors in other course you would have learned, okay? And then we do in the control part, we need to do the control for stability. We also need to do the trajectory planning. Chichikan did some trajectory planning for you, but in the computer, you need to include all these parts, okay? In the computer. Strange. Oh, sorry. It's one point. So this in the computer, you basically need to do all this, okay? And I share with you the different controls, and then that's our techniques. And then this is the robot who give you the position, velocity, and then with the feedback, the sensor in the controller, based on the trajectory generated, theta d, theta d dot, theta d double dot, then you can do the control design. When you say the controller, you say the PID, adaptive or Lyapunov. In fact, you can enlarge and more abstract and fuzzy logic, neural network control, and then you can take it as a decision making. Okay, and then we talk about stability. I give you first this is mass spring system with a damper. We introduce the stability. This is the model. Hello, I said it's my time to talk. If you continue to talk, better leave the room, okay? Is it my time to talk? Can I talk now? Thank you. I respect you, the better respect me, respect your classmates, okay? When you are talking, your classmates cannot hear me. Can you say sorry? How about you? Thank you. And the most basic criterion in designing a control system is to ensure that the resulting closed system is stable. And I have many people working control with me. And I said, yes, this stability is important, okay? As in a classroom. And when I'm talking, I really want a stable environment. So therefore, people can really listen to me. And but then after stability, my whole purpose is not for stability. It's after stable, then we go for performance. I really want you go shine. Unleash your potential better than, you be the product of NS, okay? Okay, so that's actually, earlier I said here is performance, okay? After stability, then you go for performance. And subsequently, here is you learn that I have the prerequisite. When a system of this given to you is S squared plus A1, S plus E naught equals 0. And then the poles of the system is given by this. And this is actually imaginary numbers, right? Could be. And then so you have this imaginary. If the pole, your solution is on the imaginary, the guy is oscillatory. And then because don't consume energy, don't generate energy, and then just doing oscillation. For mechanical system, you have the mechanical, clock vibrating. For electrical, you have a LC circuit. You don't have resistance, okay? And then when you have resistance damping and you consume energy, the system becomes stable. And of course, if you keep pumping energy into it, then the system becomes unstable, okay? And then this, if you're really serious on stability, I think you need to study far more than this, because for this one, I'm only for robots. I just give you the basic definition, okay? And then this stability, and then subsequently for robot, I want to, for performance, and then I include this is my force. I want to control my robot. And so this is the force. How do I control it? Then, one is your physical understanding, intuitive understanding. You see if the robot moves too fast, I damp it, this is your intuitive understanding, reasoning. And then after your reasoning, you need to put it into mathematics, and it gives you more insight. And nowadays, many people I'm leading the AI challenge in one group. Singapore got an AI challenge. I'm leading. Many people start talking to people in physics. School computing is leading on AI. But then now they face a problem. AI not secure, robust, safety, all these issues comes. When it comes to issue safety, you must link it with the physical world, okay? Otherwise, the guy keep talking nonsense. So when you link with physical world, then you know this guy talking nonsense. You can eliminate that solution. Okay, good. And then so here we added the force. And to bring the system back to the equilibrium position, that is, you want the XD equals 0 XD. In fact, I said XD, you can push the XD equals a constant. And then XD dot is equals 0, XD dot 0. This can be, if you have a force, you can bring the spring anywhere you want, okay? Okay, I can put XD equals D. And then the PID control. You all know PID control. You assume, suppose that position, velocity, acceleration are all measurable. And then we can construct well-known PD control, PID control. Here, You just use the, I did not use the acceleration, just a simple PD, okay? And then you check minus kpx minus kvx dot for position regulation. Then closed loop stability. You heard a lot about closed loop. Mathematically, do you know what does it mean by closed loop? Mathematically, you substitute this f into this equation. Then you form an equation only in terms of one single variable, x. This is called closed loop. Then the closed loop, then you do, last time I said massage. Then you do rearrangement. You massage the thing into, or simplify it. You have mx double dot plus b plus kv x dot plus k plus kp bracket x. Then you start to see, you say, Sam, then I know this. This one can equally write as x double dot plus a1 x dot plus a naught x equals 0. And then the same here, I already explained to you, right? You start, yeah. And anything, if you see 3 times, you would remember. Nowadays, too many informations, I really, you start to repeat something. I want you to see the same concept at least 3 times, okay? Because, all this, I really don't need to teach this. Deep learning, when you, first training, you learn 50%. Second training, you learn another 50%, 25, you have 75. In another training, you got 87.5%. You're almost there, okay? So I'm doing this. So you see this, anything I can transform into this. Again, here, I can transform this. Good. Then this stability, you all know here. You know how to make it stable. And then subsequently, you can say, by choosing our control gain, Kp and Kv, we can make the closed loop system appear to have a second order behavior. Appear, okay? And then we use appear. Actually, to reality, it's also indeed second order, okay? So this is the system, and then you have Kp, Kv, and then the equilibrium position xd equals 0, xd dot equals 0, xd double dot equals 0. Then you form your closed loop. Earlier I said here you have all this stuff are measurable. Here you have xd double dot, okay? And here you don't need xd measurement for this PD control, okay? But for some control system, if you really want high performance, you push for the limit. I know some research paper assume xd double dot is measurable, okay? X double dot is measurable. And so that's why I assume there they are measurable. And for PD, we don't need, okay? And then, this is actually very straightforward, right? And then the control law partitioning. Another method is the same system, m x double dot plus k x dot. Now you add another perturbation, or kx could be spring. For the open loop system, okay, you have kx equals f. For this one, another control method, you have this. For this system, you partition into 2 portions. One is model-based. Model-based, you do your control design based on the model, and then a server portion. So for this one, the model-based, you try to do based on this model. And you want to convert into a simple double integrator, is it called double integral or unit mass system, okay, for simple server control. This is the basic idea, and I show you how it has been done. So the model portion, you assume your function f equals alpha u plus beta. U is a new input for the transform system, and this is your system. And then so such that I want f substitute into here, design alpha and beta such that the system become a unit mass system. Because for unit mass system, I know how to do PID control. So the idea is, because this guy so complicated, and I don't want to manipulate it one by one, can I use a model to f, let f equals alpha u plus beta, such that I obtain x double dot equals u. And then you substitute x double dot equals u, you found you need alpha equals m, beta equals the rest of the system, bx double dot plus kx, and then the system become a unit mass system. And this is, Yuxiang, this is what I had been telling you. You have been on optimization control. Everything you do optimization, you don't know others. Okay, so this is simple PID, simple controller partitioning, and then I can do this, and subsequently we can do adaptive control and self-organization, and then you move yourself away from optimization. Okay, good. And then you in your pocket you have so many goodies. Okay, any part you see, for example, for the modeling, I have a Newton-Euler formulation. And if the robot is very simple, I use Newton-Euler formulation. If the robot is more complicated, I use Lagrange formulation. If the robot is too complicated, you say, Sam, I really don't have the energy, then I use my neural network to do the computing. Okay? I threw the job to computers. I'm not going to waste my brain cell anymore. Okay, good. And then for this one, the same idea is you convert simple. Here you still use the KP, KV. You are using this not systematic. This actually changes. For different M, you need to change different KV, KPs. But when you come to here, after I design alpha, beta, the system become this. Then my PID, PD control become much simpler. So this is the system. And then I use the alpha, beta to transform the system to a double integrated system. This part become this one, okay? For the ECE students, you know the circuit, the interface and impedance, input-output impedance. You can see this one as a circuit. You know, you see, you look at the circuit from this part, then you have F and X dot. Then I alpha added this part of the circuit, bridge, then I see the circuit as X double dot equals U. For mechanical system, I think you look from system point of view, you can also do the same, okay? You got it? Then if you look at this, you start to see the deep learning is also this structure, okay? Then if you, lecture one, or the other, 3 years ago, I met a Cambridge law graduate. We were having dinner, and then we were talking. Even though she was in law, I was in engineering, but we really had a good evening. We changed everything, we understand each other. Because come to individual domain, then it becomes domain knowledge. But you elevate it to the higher level of abstraction, they're all the same. Do you follow me? Okay, good. So this is the mechanical, then come to circuitry, then use this pattern, explain to you the deep learning, okay? And actually one of the students was helped me with the mathematics. I was stochastic. I was also explaining to her, to the undergrad, how the most modern deep learning related to the mathematics, okay? Okay. Then you see for the sum x double dot equals u, and then I can assume u equals minus kv x dot minus kpx. This one you already know. Earlier we did a 2 PD control already, you know already, okay? Here, the idea is because the system is unit mass system, and then my choice of kv, kp would be independent of system parameters. This is the beauty of this PD control. Then your system, in life, no free lunch. And then your controller is independent of system parameter. Somewhere must have used system parameters. Agree? As you are so close to me. You are my buddies, okay? And you are so close to me. So somewhere must have used. Where do we use? Where do we use system parameters? We use the transformation. Okay? Okay? This is system parameters, alpha. And then also the beta, bx. We hide the complexity inside. Good. And I really work with many students. And actually, if you are Singaporean kids, you learn my qubit. Okay. Develop a software. The software, if you write a sequential long code, you would bury yourself. So theoretically, you need to wrap up to make it simple. Okay. So here, for complex system, I use this alpha, beta. I made the system, I hide the complexity. Do you follow me? And then it become module, and then become this. Yuxiang, you got it? I hide the complexity, because you are doing research with me, okay? Okay. And then with this system, KV, KP, because mass is unit M, then my KV, KP is independent of for closed performance, is independent of the mass and system parameter. But then where the system parameter I used for the transformation, give me the idea is, sometimes the idea is very good. Give me any nonlinear system, I can always find a method to, under the certain condition, convert into the mass system. It's a very good idea. Do you agree? Any system, you can do the same transformation. Okay? I see you got it. Yeah. When you are attending, if you lost, you say, Sam, stop. Explaining, you can do that. I do interactive teaching, okay? Okay. And next one, you say, Sam, you silly. You know my robot should be follow a trajectory. You only teach me only at a position. That's a silly robot, right? Okay, good question. We make sure the robot becomes smarter, okay? So apart from position regulation, you hold the thing here. We are also interested in tracking control, trajectory tracking. Assume the desired trajectory is specified by xd, xd dot, xd double dot at all time, t, and then the defined tracking area, E equals xd minus x, and then you have E dot equals xd dot minus x dot, E double dot equals xd double dot minus x double dot. This is standard, right? And then the corresponding tracking control law, you have U equals xd double dot plus kve dot plus kpe. And then the closed loop area equation, I already explained to you what is closed loop. You substitute x into this equation, x double dot minus u equals 0. So you substitute, you have xd double dot equals xd dot equal this, right? As xd double dot equal this, so you have this equation. Now you understand that. Now you understand the system why you need to have this xd double dot here. If you don't have xd double dot here, you would have this would not be equal 0. Okay, and that's the idea. And you can take the xd double dot as some kind of feed-forward control. You see, when you are, if your friend is running ahead of you, you want to catch up with him, you need to do extra work. Do you follow me? It's feed-forward. So you can imagine that's the feed-forward part, okay? Okay. And this is actually KVE dot KPE is a closed area, okay? Okay, then. Now, once this, you have this equation. And for this equation, you see, Sam, earlier you use x, this is E, it's the same. And then you can actually still, you got this part, x, okay? This use E, they are the same, okay? And then Now the system become this. So this is for trajectory training, xd dot, xd double dot is now equal 0. Okay, and then this is trajectory control. Okay, and you can, that's why earlier I was saying for control, for the computer control, you need to, in your computer, you need to include these two parts. This is from me, this part from Chu Chi Kang, okay? So this part will all be digital computing, okay? Okay. And then another one, disturbance rejection. Just now, I was teaching, my two friends were talking how disturbances, right? I'm sorry I use a bit strict language, okay? But then, thank you for your understanding. And then you see this is the system. You have disturbances. And then for your system, you want to be stable, but then in life, you cannot be so stable. You must have disturbances. And then disturbances, actually, I constantly disturb my students. And then you move around, running around, okay? As long as they get the job done, physically they must be healthy, okay? So I really appreciate my students agree with me, moving around, they become more healthy. Now, this one actually, the disturbance cannot be too big. If you have an earthquake, sorry, okay? Yeah, the earthquake is too big. The aircraft flying, but if you have a big storm, and the aircraft cannot, okay? So that's why when I'm talking, you can talk, really I cannot hear. I'm okay with you, okay? But when your volume too big, then disturbance, so your disturbance must be less than alpha, okay? In the alpha, I cannot hear, your close friend can hear. I'm actually quite naughty as well. If a friend beside me or ahead of me, I write notes, okay? And I don't disturb other friends. Do you follow me? I write notes. Okay, good. So now you understand disturbance must be bounded. If I'm bounded, we don't talk about stability. The system already out of control, okay? Okay. So then steady state error. Steady state error means the system don't have E dot, E double dot, all dies out. You only have KPE equals F. So E would be equals F over KP. Do you follow me? You see the KP is this, you see if you have disturbances, and then the error, if I teach to now, this would be error. If disturbance 0, then error equals 0, okay? Okay, good. The effect of integral control. You have learned a lot of integral control. So I add the integral part in, and this would be integral. The integral term is added to direct steady state errors, okay? And if F is a constant, you know the error E would eliminate, okay? Over the years. You can think of yourself, you keep making the same mistake, but over the year you keep adjusting. One day, suddenly you remember as a child, okay? You think, oh, yeah, last week I made the same mistake. Then you would automatically adjust, cancel that offset error. You can think your life, okay? And then for stability, I think earlier I said the system are nonlinear, right? The world are nonlinear, but we keep teaching linear system. And somehow I said there's something wrong with that. Luckily, we have nonlinear control, ChatGPT, all this. We can do nonlinear control now, okay? And we know we can do more fancy stuff. But in the old days, engineers don't have so powerful computing machine, but they still need to run the machine. What they do, say, for example, stability. We do integration. We do differentiation. So if F is constant, then I would have E to the third order, KV E dot dot KP E dot plus KI E dot. And this would be in the Laplace transform, would be S cubic plus KVI squared plus PS plus KI. And for this, you see, you have 3 poles. 3 poles, what an engineer can do, I split into one single pole, and I have a double pole here. And then, if the position minus P1 is much further to the left than on the half plane, then the root of this S squared plus S plus B, and actually the dynamics of this guy can be ignored. So in all this engineer higher order system, I use the lower order to approximate it. Do you follow me? Then I use lower, so second order. If this further to left, the system can be approximated by second order. If you see some, what if the other way around? This one is these 2 poles further to the left. Then the system can be approximated by first order system. Okay, good. And then this is if this, then second order would be dominant. Then you only control the second order system manipulate. And why nowadays computing power become so powerful? That's why we don't need to do simplification anymore. Okay, you are doing research with me now. So much computing, I don't care. I don't need to separate approximate second order. Okay, I just compute the 3 order. Okay, good. And one thing you are helping me with me now, you know the computing, whatever we taught in the old days needs to revolutionize now, okay? The textbook was written 10 years ago or 20 years ago. It was written based on that time when the computing power was limited. And then with nowadays computing power is so much, if you go for performance, then you don't care about the reduced order. If your father reach a sub-project, you really want to push for high performance. But on the other hand, if your budget is limited, you still do the same way, okay? If your budget is limited, you can only afford a smaller car, then we do this. Okay, good. Then the learning outcome, understand the principle of control system and controller partitioning, and understand the concept of trajectory following control, disturbing rejection, and stability analysis. Okay, and so this idea is I want you to be able to apply the controller partitioning to design control system. Why? Because controller partitioning is very systematic, okay? And after this transformation, my closed-loop performance is independent of the system parameters. Got it? And I also share with you the stability use simple. So questions? Any question? No question? Any question? That means either you understand very good or I explained good, right? So we are all doing good, right? Okay, good. So this is the first single, the fundamentals. Let's do the single joint. After I prepare you the fundamentals, PD control, controller partitioning, now we do the single joint. Then the single joint, each joint is controlled by a motor. Okay, here. Many industrial robots are DC, direct current torque motors, which consists of stator, rotors, and armature. This is our high school stuff, right? And here, you know, when I teach some school computing, have a problem, I need to show them here. Glad we are all EE or ME, we all understand this, okay? And then here is basically this here, north and south. And then this is electric current. Then their force would be generated, okay? then the motor would be start to turn. Okay, generally the relationship between the current torque produced by this tau equals KMIA. The current is bigger, the torque is bigger. And then when the motor rotates, the voltage developed across the armature. The voltage generally for a given rotational velocity is back EMF, okay, constant, this EMF, electromotive force. So V equals Q E theta M dot. And I know if you don't use it, you've forgotten that, but you definitely still remember this, okay, in your high school. And then the electrical circuit of the armature is shown in this figure. So this is the motor, this is applied voltage, you have a resistance, you have inductance, and then the circuit would be described by this inductance d over dt IA plus RA IA equals VA minus KE theta M. This, do you still remember, this is your high school we learned, right? Agree? High school we learned. And the net effect that a low-pass filter between the requested voltage and the output torque. Output torque is Tm, Km. So you convert into tau m, you found each corresponding low-pass filter, okay? And then assume the motor inductance is negligible. The inductance here is very small. Then I can neglect it. The dynamics part, I can neglect it. So then the system would be VA equal this guy plus this guy. So I have this equation. And then this equation here, because tau m equals Km IA, then I have IA equals Tm over Km. Okay? And then here, this one is you can take the pure torque source. And here you can have a viscous friction. This is back EMF. But mechanically we know the viscous friction. You can later, this part you can lump up with the friction, okay, together. And then come this part. This is the motor. After the circuit, you're going to drive the motor and with a gearbox. The gearbox, you are going to drive the load. And the motor, you know it's your, you know that the motor turns at high speed, but then the load moves at low speed, right? A small motor turns speed after the gearbox, and the force is amplified, then can push a low, a heavy load. You all drive, right? Oh, no, sorry. Your bicycle, you know you can change gears. You go to mountain, you change to lower gear. If you are driving, you pick up speed, you use a lower gear, right? And if you drive automatic cars, and you know you drive on a flat road, but if you go to mountains, you need to change to different gear. Do you follow me? Okay, good. And then I is the load inertia, IM is the rotor inertia. This is the gearbox. The gear ratio, you have theta m dot over theta dot equals eta. This is usually larger than 0, in the range of 100, okay? This is in the range 75, 100, and then this tau m. And then, so you can find with this ratio, the gear ratio eta causes an increase in torque and a reduction in speed of the load. The speed eta larger than 0, right? Larger than 1. So there you have theta dot over equal theta m dot over eta. So this speed have a reduction. But the force, you start to see, if tau m is 1 Newton, and eta is 100, you have tau is 100 Newton. Okay, good. Nowadays, all the cars become automatic. If you're driving a manual car, you wouldn't know first gear, second gear, okay? And then you wouldn't know you can have a feel. And if you're riding bicycle, you can change gear, you can have feeling, okay? So a torque balance rotor gives actually this. A torque balance at this rotor part plus tau m. So the tau m would be equals this m times theta m double dot plus km theta m plus this torque, from drive the load, and then actually on the reverse side, you have tau to the load over eta, okay? And then the tau is given by I theta dot dot plus b theta dot. Then you have this. Then I can convert, because the theta, I have this equation. I substitute this equation here. Then I would have when you drive the motor, you have equivalent mass as m plus I over eta square, and then the viscous friction bm plus b over e square. Okay, you have this one. Now from here, this is actually equals time. If you, many of you, I think the boys prefer to play with motors, robotic fish. Jiadong, you play with robotic fish, right? Your robotic fish, you need to have motors, right? Do you have motors, electric motors? Your electric motors, for your control from this equation, you can see if you have a gearbox larger than 100, this is 10,000 already. So if the load, you have any load, after divided by 10,000, this becomes very small. It's negligible. Do you follow me? So you only need to control the motor's load is okay. Happy? So that's why I ask you not only doing design, mechanical design, you do some computing. You do some computing, you can see very clearly, okay? And when I was at Imperial College, my supervisor said I can do whatever I want. So I started doing a lot of analysis. In the lab, I have AGV, automatic guided vehicle, robotic manipulators, and visions. So I do all the analysis of different type of robots. And then, actually, one day the robot was not stable, quick wiggling. And I went to talk to them. I said, why the robot crazy? They said that they want to improve the performance. They installed the tachometer on the load side, and the robot becomes this. I said, if you want to install on the load side, then your feedback gain cannot be too high. If too high, the system becomes unstable. He said, how do you know? I said, I did my mathematical analysis already, okay? Now you know the mathematical analysis is important. Do you follow me? Okay, good. Then you say, Sam, this is you put it on the motor side. What about on the load side? On the load side, you assume this tau m, this now I convert this tau m to tau side. And then I would have I equals eta square m and times theta dot double dot plus b eta square bm. And then again, now you start to see this on the load side. If eta square is really 10,000, then the m could be still dominating the corresponding moment of inertia, okay? And then this is effective inertia, this is effective damping. And this is when you have a gearbox. Here I made some remarks, okay? And they say, Sam, how do you derive theta m equal this? I said that can be easily derived. you assume you have this two gearbox, you have the teeth together. You have teeth together. When you move, okay, doing this, then you can find the distance they traveled should be the same, okay? So that S equals R theta, and then corresponding RM theta M, okay? And then the force torque, because the force here, they are all equal, then you have a tau FR, then eta equals theta. You found F equals tau R, tau M, they are equivalent, then you can find all the equations, okay? Here, F equal, S equal, then the equation you can all derive it, okay? Okay? And many researchers, postdoc and PhD students, they come, they found, I can explain to them the concept very clearly, okay? And the rest all can be derived. So here you start to see, after you found this S equal, F equal, then the rest you can all derive. Okay, good. I put eta equals 1 here. If eta equals 1, you don't have the gearbox. And then this direct drive robot. Direct drive robot, when you don't have the gearbox, the gearbox actually have, when the gear is too high ratio, then the teeth of the gear become flexible. Do you follow me? Become flexible. Then this part they call the flexible joint robot. I can show you. You see, each joint, you take it as flexible, okay? And you can find this is actually circuit flex joint, okay? And then, but then to control that kind of robot is much, if you really want, the best if the frequency is low, then you don't excite the spring. And if you see you need high performance, then the spring need to be over that, then you need a more complete control method, okay? And I Professor Mark Spohn, or many others did a control, and you can drive over the spring. And if you don't have a gearbox, they call it direct drive robot, then the robot can really move at high speed. When I was at Imperial College, my supervisor, he's very rich. He drives Rolls Royce, and then the president of South Korea visited my supervisor as well. He was designing direct drive robot for the manufacturing, the chips manufacturing actually, because it's very accurate, okay? You use the gearbox, it's not accurate. So that's why I know the direct drive robot. I was playing with that drive robot. That motor at that time, I think China cannot buy. And, it's a control item. But recently, I went to China, I started to find many companies can produce that motor already, okay? This direct drive motors I found. I think in 2010, China still cannot produce. It's in 2018, I found many people, many companies, not only one company, many companies can produce. That's why the many robots are produced in China now all over the places, okay? Okay, good. To ensure the motion of a robot link is never undamped. When undamped, you have oscillation, right? The value for I should be the maximum value IM. And then this choice will result in system that either critical damped, eta equals the cosine equals 1, or over damped, So the system maybe moves slow, but don't do oscillation, okay? Okay, the system is modeled under the assumption that rigid linkages. In reality, every element has a finite stiffness. However, if the system is sufficiently stiff, natural friction of unmodeled resonance are very high and can be neglected compared to the influence of dominant second pole that we have modeled. Earlier I said earlier I said that the system you assume as a second order, right? Then the unmodeled dynamics, you don't excite it, so you are okay. Do you follow me? You don't excite the spring or higher order, your frequency, natural frequency low. Then give you a rule of thumb in that if the lowest structural resonance is the omega rest, and then we must limit the closed loop natural frequency according to omega less than half of the structural resonance. And then you don't excite it, okay? Do you follow me? You know the building have a structure, okay? If the earthquake is smaller than that, we are safe, okay? The vibration, do you follow me? A structure, good. Typical industrial manipulation have a structural resonance in a range of 5 to 25. So if you have a gearbox, you see your omega need to be maximum 2.5 hertz. Then you know the robot move very slowly, right? But then direct drive robot can have the lowest structural resonance because you don't have a gearbox, can have 70 hertz. That's why that robot can really move fast. Speed is important, okay? And in the old days, we remember, nowadays with ChatGPT and all this computing out, I think we need to learn your learning pattern. That's why I keep the same concept refer 3 times. I'm trying to teach you a new learning pattern, okay? And then estimation resonance frequency. A rough estimate stiffness is singly can be modeled as a cantilever. For example, for rounded hollow pipe, you know the hollow pipe round, and then the stiffness can be given by 3 pi e over 64L cubic. This D is O is the outer diameter, Di is inner diameter. Okay, they have those in the mechanical material science. You do this. As day one, I shared with you, I'm working with Kostya on the Institute of Functional Intelligent Material. So the material is important. Okay, if you are doing robotic fish or soft robotics, you know this is important. Okay. And then if square cross selection hollow beam, then you have this, okay? W is the outer width, inner width. And approximate natural frequency can be obtained by equivalent simple spring mass system, omega n equals square root k over me, okay? Me is the equivalent mass displayed in vibration here, okay? The equivalent mass, not this mass. It's equivalent mass. Okay. And then this Win Book, he's very senior. I think, I hope he's still alive. Okay. He's very senior. I met him, I think, 20 years ago. He suggests to use a lumped model of mass to roughly estimate the lowest resonant frequency, omega n equals square root k over 0.23 m. Here is 2.3, right? Okay. And then now the control of single joint. So we have done our model, right? From the motors, the beams, gear from the motors, the circuit, the beam, the gearbox, and then the approximate beams, we obtain the models already. Okay. So to obtain the model, usually we have made the following assumption: the motor inductance can be neglected. The motor is a pure motor source, and take into account of higher gear ratio, you have the inertia, equivalent inertia, and the structure of flexibility are neglected because your control servo loop gain is below this natural frequency, resonant frequency. Okay, and then we obtain this dynamic model, M plus eta square Imax plus eta square M, and then theta double dot plus KB plus eta square BM theta dot equals tau. And then how do we control system design for this? You say, Sam, this is easy. This one you taught us controller partitioning, right? Yes, good idea. Okay, so because of this, the control design carried off. So now this we say control of a single joint. Okay, so after we have the model, then we do control. Then the control, this is the model. We do controller partitioning. We found alpha equals this M, beta equals the whole lot. Then the U equals theta D double dot plus KPE. Then I found my closed loop area equation. Then KV equals 2 square root KP, and KP equals omega and a quarter of omega resonance square. Then I design my closed loop stability. Happy? Okay. And then the learning outcome is understand the purpose and method of single joint control, and know the rule of thumb in the limits of closed loop natural frequency. Okay. And basically, you need to know this must be less than half of the natural frequency, okay, structural resonance frequency, and then the controller partitioning, okay, be able to apply single joint control simple system, okay. So with this, I give you time. Give you half an hour for your dinner. I see you later, okay. Shall we begin? Okay. Welcome back. Let's begin. And, for the dynamic part, we make it from complex to medium complex to simple. For control, I do the other way. I do from simple to complex, okay? Then your brain would be got used to either complex to simple or simple to complex or medium all the way. I can all handle, okay? And then you must get your brain fully excited, okay? And I was talking to Wenxin and Yuxiang on the way during the break because they are my PhD research fellows. And then we need to talk, arrange a lot of stuff. I said, when you are doing research or when you are doing study or when you have something of your love, for example, you have a cat or dog, okay? When you think something, you cannot keep thinking, day and night thinking, make your neuron in your brain burned. Do you follow me? When you work, if you don't work, your neuron is disconnected and you don't learn stuff. But if you learn, keep learning, and then your neuron is so tiny, you keep learning, you don't go sleep. Not enough power. You got enough power, you connected. Not enough power, lose. Got enough, and then you keep learning, this part could be burned. Do you follow me? And then you could got your sickness. So if you cannot think, really cannot connect it, you go to sleep, have good sleep, tomorrow morning have a cup of coffee, and talk to your supervisor, talk to your friend, or talk to yourself again, okay? Make sure your neuron is healthily connected, okay? Okay, good. Now, I have shared with you single joint, or called independent joint control, was carried out assumption. Each joint is considered independently. I share with you each single joint control, right? You have an unlinked robot, I can control the joint one by one. And the inertial seen by each joint actuator is constant. We made that assumption. But in reality, I'm sorry, the robot needs to pick up stuff. The robot change configurations, and then the equivalent method do change. And then so the approximation results in linear control, which subsequently results in non-uniform damping through the workspace and other undesired effects because the company are not compensated for. So, I put a nice robot here. You like this color? Okay. And the color. And then because each joint considered independently, and you did not consider the coupling, and then the control performance no good. And in the technical terms, they write like this: no uniform damping through the workspace and other undesired effects because the coupling are not compensated for. So then you say, Sam, what if I compensate for the coupling? Then it would performance would get better, right? Okay, let's do decoupling. And then 3 advanced multi-joint control technique will be introduced here to eliminate these assumptions. And I will share with you 3: complete talk method, Lyapunov method, and adaptive control. Okay, and then you see how the file organized is this 3.3 is complete talk, and then in another 2 files would be Lyapunov adaptive control. Okay, this adaptive control, I would put a neural network here as well, and because neural network structures, actually the deep learning need to work with my adaptive to improve the performance. Deep learning is in a control community called offline training, and then this online training. If Yuxiang Wenxin, you really want to be breakthrough, you can think about it. I talk to you, okay? And then this, and then so I shared with you controller partitioning. This controller partitioning is basically the beginning of complete talk method. This also, or you can say complete talk method is also called inverse dynamics method or controller partition control schemes. Okay, and this actually, when I put the idea all the same here, when you read in the literature, you don't be confused by the name. You see the content. So because the idea they are developed from different field. In control, we have electrical engineering have control, mechanical have control, chemical have control, right? Now the material science would have a control soon, okay? Control would be going to the material science. So they mean the same. So the general idea is compute a nonlinear model-based control law to cancel the nonlinearity of the system and render it, transform. You see GPT, right? Chat GPT. GPT means generative and pre-training transformer. This is transformer. You can see rendering, I say transform, okay? So transform it to a simple double integrated system. If you say, Sam, I don't like double integrated, you say transform it to a simple unit math system, okay? Double integrated system is usually by mathematicians. Unit math system is by engineers. Okay, in the control engineering, there are many applied mathematicians join us. So they use double integrator. Okay. Okay. So and now to link with the most modern technology, the rendering I think transform. Okay. So then after you have done that, you design simple linear controller for simple linear system. Linear system, we have plenty of tools to handle, okay? Okay. So for any real freedom robot, the dynamics are described by d q dot plus c q dot plus f of q and plus g equals tau. Then d q dot, this is inertia, and c is the Coriolis and central group forces. F is the friction. Okay. G is the gravitational. Okay. And then so you basically have a complete system. And then you can define the H. You lump the whole lot, put it here. You can say the equation, you can write d dot plus H equals tau. Okay. And then for this one, to do control system design from the controller partitioning, I think you should have some idea now, right? So what you do, from the most intuitive control design scheme in the complete talk method is you delete your u tau equals alpha u plus beta, And you choose alpha beta such that the system, when you substitute tau into here, the system becomes Q double dot equals U. Do you follow me? And then how you can achieve that? You compare the two equations. You would find alpha equals D, beta equals H. Then you achieved this. This is the same as we did for the controller partitioning. Do you follow me? Okay. When I see you last week, I said, I remember when I was teaching, I see some of you got tired. I said, when you got tired, you pick up your pen, draw a picture of them, right? And then if you are really tired, you can try to substitute tau into this equation. Then you write canceling, you would get it. Okay? You can simultaneously work with me. Okay? Then your brain would be more engaged. You got more stimuli. Good. And then when for this system, Q double dot, earlier, X double dot, we know how to do it. X double dot is a scalar, one variable. Q double dot is a vector. Okay? But then Q double dot is, even though it's vector, individual vector that I put together is the same. So what you do, I do the U equals QD double dot plus KVE dot plus KPE. And then KV, KP are diagonal matrices. KV, KP are diagonal matrices. So that means the corresponding, even though I write the closed loop error equation in matrix form, but in joint basis, they are actually the same as I did it for single joint robots. Is that okay? So this is for single joint robot, and put it in matrix form would be this. But actually, after the nonlinear transformation, I made it into a simple linear system. So I give you this system. This system, after alpha beta the transformation, and becomes simple linear system. The simple linear system, I can do the simple linear control design. Easy? Easy, right? Easy? Is it easy? You're still catching? I thought you ran very fast. So which part you need me to explain further? Or maybe you need to read a little bit more. This is a single axis. I write in matrix form. Here I write, you know the KV, KP are diagonal matrices. So when I open the matrix, I become individual joint. Right? Then once I come to individual joint, and then you'll still remember my individual joint. We do the here alpha beta, and then the for the X, this is single joint, and for the fundamentals, we also did the alpha beta. Okay, and this is also alpha beta. Okay. Now alpha beta. So I repeated at least 3 alpha beta now. Okay. Okay. This is the fundamentals, alpha beta, the transform, and single joint. Single joint. I did 1 alpha beta, and then for the multiple joint, I have the alpha beta. Okay? This is easier now. I repeated 3 times now, right? Should be a habit. I'm pushing my staff to build up a good habit. For your body to remember, you need how many days? A habit to be built. Your body knows it. How many days? How many days? Wow, good. How do you know that? You read it somewhere. Did you practice? Okay, good. You try, okay? If you know the theory, and then you try to see whether it works or not. And then again, when I showed you the theory, and then you try whether it works or not, okay? If you know the theory, then you try. Nowadays, I also give the theory and to myself and to my students. And some students accept my theory very well. They work with me. Indeed it works. Some people reject it. So, no, it's all nonsense. Then, of course, don't work with them, okay? And then, so if you believe in 30-20-20, you try it, okay? Okay. So now the alpha beta works for you now?
How can we choose alpha and beta? It is system parameters, right?
The system is D, H. This is our robot design, we know it. D, you know, during the robot dynamic modeling, the D is designed. The D robot, the weight, the length, we know it. Especially, for example, this is the robot we designed, the CAD CAM we can compute. Yeah. Oh, you think too far. You really think far. Then you say, when the robot pick up unknown weight, then my dear, I don't know. Okay? If it don't pick up something, then I don't know. I think if a stone, I ask you to pick up, you thought it's just stone, and then but if it looks like a stone, but it's all empty, it's a paper, you will have a good laugh. So because your estimation, okay? So subsequently, I will teach you adaptive with how you can adaptively adjust, okay? You think too fast. For the time being, we assume H is known, okay? Now it's okay? If alpha H are known, then everything is beautiful, right? Good. In a known world, everything is beautiful, right? You know me, I know me, we are all friends, right? So for the time being, we know everything, okay? Okay, good. Now, if we know everything, this is beautiful, right? You see, sometimes I see my engineering students, have always think, not happy. But I found my mathematician friend, they are over every day they were happy. Because to them, the compute, every parameter is known, every example they can show. Do you follow me? But for our engineers, say, the weight is unknown, the true value I don't know, I have measurement noise, I have this disturbances. But for the mathematician, the world is so beautiful, I can beautifully describe. Do you follow me? So I hope, we assume yes, everything is known. At least we are happy first, okay? Okay, good. I see you are happy, right? Okay, good. And then I make a few remarks. The ideal performance represented by this, okay, is unattainable in practice due to many reasons. One, the most important being inaccuracy in the manipulator model. And then discrete nature of digital computer implementation as opposed to the ideal continuous time controller. And also, third, I could say disturbances, okay? And so, but at least we must get start from somewhere. And then so, if the model is accurate, computing is continuous, and no disturbances, this is good, right? Good. Then we start to handle how to handle this. Okay, how to handle inaccuracy in the models, how to handle the computer implementation, then we push our limit. Is that okay? Okay, good. Then, present industrial robot control system, because the problem is having a good knowledge of the dynamic models, there is a trade-off between complete model-based control and simple PID control. And many industrial robots still have a tau, QD dot dot plus KE, KVE dot plus KPE plus KI integral E dt. Okay, have simple independent joint PID control, and this is many industrial robots still doing this, and it works. Why it works? it works, okay? Because people thought, PID, P is proportional, and derivative, I introduce damping, integral, I do the historical understanding, right? And then, so it works. And then come to complexity, then for the complex nonlinear system, why it works, linear system cannot explain. Later, when I introduce Lyapunov design, you will say, PID indeed works. So in the linear dynamics theory, this one, even though is linear control, because for linear control, the system nonlinear, we really don't know how to explain, okay? And in the linear world, and in the linear world, I can only say proportion V introduce damping, KP proportional. Hopefully it works. Unless you use the linear symmetry, the pole placement or LQR or H infinity, okay? Unless you invoke those things, but still, because we are controlling a nonlinear system simply want to handle the nonlinear directly, okay? And then advantage, simple and easy to implement, robust because decentralized control implementation. Disadvantage, no decoupling is being carried out. The motion of each joint affect the other. You have the joint, this motion affect this one, and then this motion affect the other two, okay? And it's impossible to select fixed gain, which could dampen the response for all configurations. And because the configuration, the equivalent method do change, okay? And usually average gains are chosen, which approximately critically dampen the center of the robotic workspace. And all this engineer are smart. If this is the workspace, then the robot most of the time concentrated working here. So he put the gain here is optimally tuned. Other part, if you have any shaky, any errors, don't affect much. But this part is properly tuned, okay? Okay, good. And the additional gravity, since the gravity term tend to cause static positioning errors, some robot manufacturing includes a gravitational model G of P in a control law. So they add this part. And this is approximate. I put height is not the true one. Is because of the manufacturer, I know my robot, the heavy, but the robot is going to pick up stuff, then that one would change, right? So the control is not decentralized in nature because you need communication between the different joints. The architecture of the control must allow communication between joint control to make use of central processor. And this earlier I said nowadays computer is cheap, sensor is cheap. You can really push to the limit. But if you really have a limited budget, but you still want your robot working, okay? And I think there are many robots that are cheap. Because customer, I only consider how much I pay you on whether your robot works or not. So then engineer also still need to cut costs down, okay? Cut costs down. So therefore, I also introduce the cheaper controller, okay? For your research, you push for, if you got loads of money, you push for performance. But if you have limited money, you push for cost effectiveness, okay? And then I want to give you a few tutorial problems. Complete torque control was introduced based on D, C, G for tau equals tau. Apply the same idea to system described by D, C, G, F, and also D, C, G plus B tau. B is a non-singular unknown, and then or M, H, or how about a third order? Okay, or could we generate to the nth order system? You see, as when I'm teaching the robot control, the robot has shown you this form, the robotic manipulator. But actually nowadays, there are too many different types of robots comes in, okay? Fish, flying robots, and then, and soft robotics, mature robotics, all comes in, okay? So I teach you a simple robotic manipulation control, but the robot actually really comes in different forms, okay? Okay, good. So this is the tutorial problem. I have solutions, and maybe I think I stop over here for you to think, and I will discuss with you next week. Is that okay for the tutorial? And later you go side because you need to absorb something, okay? The computer talk. And if I go, you start to see too much information. When your dishes or food, you need veggie, meat, bread or mix. So I give you a theory already. You see the tutorials, all these questions, and then you put into back end. Let your brain to do the back end and the computing. You can think, and then at the same time you can see what I'm going to teach another concept. If the two concepts are not correlated, you can learn things simultaneously, okay? If they are correlated, you got confusion. You always go back to, just now I was talking to you, you said, I'm still thinking, the H, how do you get your H, how do you get your D, right? I said, we assume they are all known. Then you got your problem solved, right? And then when the H and D are unknown, then we move along to see how to solve it. Okay. So, and you use the computer talk method, you see how you can handle this, okay? Then move on to the next one. Okay, for PID control, I said, how do I prove stability? I really have no clue how to do it. Because when you linearize the robot into non-linear one, you use PID to, you change the problem, because my robot is nonlinear. And when I show you here, I can show you that, yes, PID can prove that it's really stable by using Lyapunov theory. Okay, this is Lyapunov stability analysis, or Lyapunov second method, or Lyapunov direct method. And after Russian mathematician in the 19th century, and is concerned with determining the stability of differential equation. You all take the feedback control already, right? And then the control, the stability for linear system, we basically can found the solution of the linear system, and we express it analytically. And then, then the Lyapunov said, what if you give a nonlinear system equation, and you cannot solve the solution? How do you know the system is stable or not? Give me a linear system. I can find the solution. I can show you which component diverge, which component converge, right? But then come to nonlinear system, how do you solve it? So he basically tried to solve this question without solving the solution of the differential equation governing the system. And then how can we use the result to design stable control? So in general, it does not provide any information about the transient response or performance of system. There's in life, there's no free lunch. If you solve this problem, then the other problem comes, okay? So for this one, you use the Lyapunov method. You don't need to solve the differential equation, but you would have difficulty to find the transient response, okay? But then we solve the stability first, okay? And the performance, we can do simulation, do experimentation, and test until we are happy, okay? Okay. So to prove a system is stable by Lyapunov method, one is required to provide the general energy function v of x that has the following property. V of x has a continuous first partial derivative, and v of x larger than 0 for all x except v of 0 equals 0. And v dot of x less than 0. Here, Vx means the change in V along the system trajectory. Okay? And for detailed description, you see this Slotin and Li Weiping, okay, apply nonlinear control. This is the one for those people who want to work with me on control, nonlinear control. This is the first book I asked them to read. And I wrote my first book on adaptive neural network control of robotics. That's the second book I asked my students to read. Okay, why I asked them to read? Because this book is written for engineering students, easy to understand the mathematics, and then the mathematics is explained really coupled with engineering. And also for those mathematician background, to them is everything is mathematics. So through this book, they know they all also link to engineering. Do you follow me? From engineering, from this book, link to mathematics. So this book made this theory easy to understand. If you don't believe me, you don't read this book, you search nonlinear system, nonlinear control, you compare those books, compare with this book. Other books are very difficult to read, okay? If you finish this book, then you start to read other nonlinear control books, become easier. Do you follow me? So this is the book. And then it said that this V of x larger than 0, then you have this. And if V dot larger than 0, then the energy keep going up, would explode. If V dot equals 0, then system is oscillatory. If V dot is less than 0, then the guy spiral down to the Whether to the 0 or not, we need to double check. Okay, at least this guy don't blow up. Okay, and this Li Weiping, as I said to you, I went to Imperial College, he went to MIT, okay? And roughly, we are from the same university, BOA, and then, Beijing University, or not, BOA, and then he wrote this book. And then, this is a really good book. And then after he got his PhD, because he wrote the book, he wanted to become a faculty at MIT. I think they debated, and he was not awarded. But quality is really top. And then he went to Hong Kong, and then later, I met him a few times during the conference when we were younger. Recently, I don't met him anymore, and I heard he went to business. He must be very rich now. Okay. And my students are already financially independent. A number of my students financially independent, including my master students. Okay. I have in Singapore. I have 2 companies. I sold one. My second company, the student is financially independent already. And my PhD student. Last time I showed you 3 PhD students, right? At least I think 2 are financially independent. And so next one, I want to share with you the example for stability, for Lyapunov stability. So this model I showed you many times already, right? Mass spring system. And this model, we know, I showed you many times already. And then how to write state space model, you all know inside out already, right? I write a state space x1 equals x, x2 equals x dot, okay? And have this. And then for this one to show its stability, for linear system, we need to solve the poles, right? Here, you forget about the poles. Forget about zeros, okay? You forget everything your teacher taught you, okay? I'm learning Tai Chi with a grandmaster in Taiwan. He is also developing. 1 year, I think he was telling his student, you forget all about things that I taught you earlier. You do it now, okay? And I still remember. So for the linear system, when we talk about nonlinear, you forget everything about linear system, okay? In the nonlinear world, anything can happen. In the linear world, your father is rich, you are rich. Your father is poor, you are not, you're definitely not rich in the linear world. In the nonlinear world, anything can happen. Your father is rich, okay? You would be super rich, okay? And if your father is poor, you would be rich. Do you follow me? Or super rich. Anything can happen. So in the nonlinear world, we don't need to handle poles or zero. Pole zero, boring or not boring? Boring, right? Very boring. Okay, good. Okay, show that the system is stable at the origin. What do? The total energy of the system is given by V equals half mx1 dot square, because x1 is the x dot is the velocity, right? Yes. And then half kx square. K is spring, so it's the potential energy of the spring, kinetic energy of the mass. And Yuxiang, I was telling you, I said, the other guy, Nobel Prize, is energy component. Here our state is the energy storage component. Got it now? Thank you. Now you should be happy to come to see me. Your study is slow, okay? Now you can link now. So the energies include kinetic plus potential energy. Then you see the two is written, Yuxiang, this kinetic energy, potential energy is the same as the paper written for you. Yeah. So that's why I say that paper is actually not that good, okay? We engineering already solved. And then V dot equals this half, because I have x1 dot square, and then this square have cancel this half. So I have m x1 dot, x1 double dot. x1 double dot actually equals x dot double dot. And then k, this half cancel, I have kx x dot. Happy, right? We never talk about poles or zero, okay? In the nonlinear world, no pole, no zero. And then substitute the dynamic equation. This guy, mx double dot equals minus bx dot minus kx. And into here, right? So mx1 dot equals minus. So you would have x1 dot minus x1 dot bx1 dot, you see, minus bx dot, and this guy minus x1 kx, you cancel this k. So you're left with the equation. Do you follow me now? I explained step by step. You got this. So this means that the system, however it is put, but, for this system, however you push me, I always stay here, okay? However I'm put, but you push me or uncertainty, I'm always here. And then, so the system will always lose energy. And when it comes to rest, x dot equals 0. X dot equals 0 does not mean that x equals 0, okay? So then, whether x equals 0 or not, we try to see the system. X dot equals 0. If x dot equals 0, that means x dot also equals 0. You do its derivatives. X dot equals 0, then have x dot equals 0, x dot equals 0, I have kx equals 0. Then you have kx 0. Kx equals 0, if k is a constant, non-zero, then I have x equals 0. Then the system is stable. You see, for the stability of this system, I never talk about poles or zero. I never talk about solved solutions. You see, you compare with Lyapunov equation and the linear system, you can relate to Newton-Euler formulation and Lagrange-Euler formulation. Lagrange, I take the system as a whole, I get the equation. Newton-Euler, one by one, okay? You can compare with that. Got it? Your brain, you can do the abstraction, okay? Happy? You see, I don't bother to solve the equation anymore. What habit do you want to do for 21 days? Recently, there was a student, not mine, somebody in Shanghai I met, and she recently sent me email. She said, I want to go to your place to study, change your environment, and blah, blah, blah. And I found out that she's sleeping pattern not good. I started to push her, get up in the morning and then proper sleep. So now she agreed. Okay, every morning she says, "Sam, morning, Sam." Okay. So if you have sleeping pattern, let's try that one. Okay. Okay. Next one, I want to share with you this. Consider a manipulator described by DCG equals tau. Then controlled by a control law equals KPE minus KVQ dot plus G. Is this PD control? Yes or no? Yes or no? I see you are close to me. When the stuff is simple, you don't care. When something, you care much, right? So it is simple. It's quite simple, right? I cancel this. If I cancel this one, then this proportional derivative, right? Yeah. And then except that because here I made something, I want to do position control, error control. And then this I only introduced damping. I did not use E dot. I just made some simple modification. Okay. And then I added a gravitational compensation. If the robot don't have a gravitational compensation, then this. And if the robot don't have is a planary, then this is really PD control, right? Good. Now earlier I was showing you for this. So this is the control system. This control does not force the manipulator to follow the trajectory, but move the manipulator to goal position. Okay. So the resulting closed loop equation is this. The resulting closed loop. I substitute this guy into here. So I move the stuff onto the other. G is cancelled. So this is the dynamic equation, closed loop equation. DC plus KPQ dot minus KPE. And I ask you to show that this system is globally asymptotically stable. Can anybody show me using linear system theory? Anybody can show? If you can show that, I can invite you for lunch, go to the moon. Okay? Because it's non-linear system, okay? Linear system is really out. Okay, that's why I said you can go to the moon. I can bet, okay? Otherwise, I would lose. I would definitely cannot fulfill my promise, right? So this linear system is out. Then we have to handle using nonlinear system theory. In nonlinear system theory, it's actually very beautiful, very easy. Any idea? Anybody know how I can handle? I see you also very careful. Do you give any idea how do we handle the stability? I give you a hint. Here we use energy, right? Can we use the energy as well for the Lyapunov function? Can we? Let's try, okay? If you don't know, you say, why not? Right? Say, why not? Yes, good, let's go. Okay? Why not? And then for this system, we consider this Lyapunov function. Lyapunov function candidate V equals half Q dot transpose D of QQ dot plus half E transpose KPE. E is the error we defined. Now we change a little bit. Here is the kinetic energy of the system. potential energy of the system. They are all physical quantities, okay? Glad you are listening. This is important. And this one I changed. This is a physical quantity. This is actually artificial potential energy. You follow me? This is, I create an artificial area. This is artificial spring, not a physical spring, okay? And now you understand why the ChatGPT can be creative artist now, okay? He can generate a lot of imaginary stuff, okay? Okay. So this artificial potential energy, which is always non-negative, since D, K always larger than 0, positive definite, okay? And then differentiate V, this V, along this dynamics, this one, okay? Along this dynamics. And then you have this half, we did duration already, Q dot transpose D, Q dot dot. And we also need to do half this D dot. And then this one, because Kp is constant, Kp dot equals 0. So you have half, you have E transpose Kp dot. And then, do you still remember D dot 2C is square symmetric? Do you still remember? Hello, girl. I see you are quiet. You are close to me. Do you still remember? K dot 2C is square symmetric. Do you still remember? Your friend got a good habit, 21 days, okay? You talk to her with 21 days habit, okay? Do you still remember 20 D dot minus 2C is square symmetric? Yeah, in the dynamics part, property. Good. You see, she knows, okay? If next time you don't understand, she knows, okay? Okay. That's friend for. What friend for, right? You help each other, right? Okay. I see some of you sit together. You talk to each other, help each other. Okay. But when you help each other, when I'm talking, but don't fight with me, my volume, okay? Okay. So D dot 2C is square symmetric. When it's square symmetric, then I have Q dot transpose this equals 0. Do you follow me? So I can minus half 0, okay? So this equation, minus 0. This is 0, okay? When I open the bracket, this D dot cancel this D dot. I left with D, C, and Kp here, okay? Okay? This is the beauty of it. When the D dot C minus Kp, you look at this one, dC minus Kp equals minus KVQ dot. When then I substitute, I have minus Q dot transpose KVQ dot. Okay? Then I know my V dot is also less than 0. Then again, I follow the same theory. V dot is non-positive as long as Kv is a positive definite. Okay, and then next, let's investigate whether the system can get stuck. Okay, stuck in with non-zero error. Okay, and get stuck with non-zero error, because we can only remain 0 as long as trajectory that Q dot equals 0, Q dot dot 0, because V dot would be keep reducing until to a point Q dot equals 0. When Q dot equals 0, you have a Q dot dot also equals 0. Then you substitute into equation. If Q dot dot Q dot equals 0, all these elements would equal 0. You're left with minus Kp equals 0. And then you have Kp equals 0. If Kp, because Kp is constant, Non-zero, I have E equals 0. So therefore, the system is asymptotically stable. Okay. So the proof is important that explain that so some extent why today's robot works. So here the controller is a PD control plus gravitational compensation. So here, last lecture I said why PID works. I cannot explain. Now I can explain why PID works now. Right? Okay? Yes? Agree? Thank you. Wow, you are my buddy. You really agree with me. Oh, you got a strong arm. Good. And then, so you understand the principle of Lyapunov functions and stability analysis. Okay. You also know the advantage and limitation of Lyapunov stability, and be able to apply Lyapunov control design to multiple joint robots. And then the advantage, you see, you don't need to solve the equation, okay? And disadvantage, you don't know the performance, okay? Do you follow me? You don't know the performance. And another one I want to highlight, actually, I want to ask your theory. How do you design the Lyapunov function that it works wonders? How? Anybody got ChatGPT? You Google. You're not a Google anymore. Sorry. Chat. How do I find the Lyapunov function for stability analysis? I really wonder what GPT come up with. Okay. Anybody got ChatGPT with your computer now? You can check. So now my question, I ask you, how can I come up with Lyapunov function? I know this is the system is stable. How? Hello, girl. You're also a friend. And don't get scared. We discuss together, okay? So how can what kind of function do we choose? We know the system would give me good result. You see, I started with energy of the system, right? Here is the energy of the system. Here is the energy of the system. I include artificial energy of the system. And then you start to see you must have energy form, right? Then I can have physical energy of the system, and then artificial energy of the system. Then those at least give you a hint, right? Agree? You follow me? Huh? Try to follow is okay. So then I give you this question. I also left you some tutorials. You think, okay, now we need to go deeper thinking now. Deep learning, deeper thinking. You can also deep ChatGPT, okay? ChatGPT, you ask him simple question, he give you simple answer. You ask him deeper question, he give you deep answer. You ask him a very deep question, he give you a very deep answer. Do you follow me? I tried, okay? I tried. It's really he help you grow. Okay? So I start to give you how do we choose the Lyapunov functions, which candidates which gives a lead to stability. This is a good question, right? If I never give you earlier break, I give you this question, I can let you go off 5 minutes earlier. I remember last time when I was teaching, once you do, I don't know, I still got time. So with this question, I can let you go. And my answer is, before you go, is you choose, these are the energy parts, only give you the hint. Okay? Energy of the system or virtual energy of the system. Only when you prove that V dot is less than 0, then you succeed. If we did not found V dot less than 0, then you failed. Does not mean the system is not stable. Do you follow me? Because this approach is sufficient approach. If you found it, jolly good. If you did not found it, you cannot conclude the system is not stable, okay? Then you keep funding, okay? Do you follow me? Then you really need to work really hard. I think I stop here over here. I see you next week, okay? Because day one I did not give you any, and then don't forget my tutorial, okay? I also have my tutorial here, okay? And I would explain to you next week, okay? Okay, then see you. And in this week, Jiadong and I would release the project, right? We will release you, after we release, we will send you through the email, okay? Announce. Okay, then, see you. Yeah, thank you.